This is my 6th video about the best methods for converting acyl halides into ketones. In this presentation, the acylation of enol ethers will be discussed. Unlike enamines, enol ethers are neutral and do not convert acyl halides into ketenes. As with enamines, enol ethers are attacked by electrophiles at the beta carbon. Unlike alpha-haloalkylamines, however, which cannot be isolated, alpha-halo ethers can be sufficiently stable to allow isolation. These halo ethers are sometimes obtained when enol ethers are treated with strongly electrophilic acyl halides in the absence of any base. If bases are present, however, elimination usually occurs and yields beta-alkoxyenones. Unfortunately, enol ethers can oligomerize upon treatment with acids, and it is therefore usually not possible to catalyze these reactions with Lewis acids. Therefore, this reaction only works well with highly electrophilic acyl halides, such as tri- or dichloroacetyl chloride, oxalyl chloride, and similar acylating reagents. It has also been reported that palladium can catalyze these reactions, but this strategy hasn't been used very often. The main advantages of this acylation reaction are that the starting materials are inexpensive and readily available, and that, when they work, the reactions are easy to perform. No strong bases are required, and the reaction usually stops after the first acylation. Unfortunately, the scope of this reaction is narrow because only few acyl halides are electrophilic enough to react with enol ethers. This is a typical example of the acylation of an enol ether. Trichloroacetyl chloride is sufficiently electrophilic to acylate dihydrofurane and other simple enol ethers under slightly basic conditions, and high yields of the enones are often obtained. This is an example of the acylation of ethylvinyl ether with trifluoroacetyl chloride without any added base. Here, the initial product is the alpha-chloroether, which however undergoes elimination of hydrogen chloride upon heating. Because the trifluoroacetyl group is very electron deficient, even the less volatile anhydride of trifluoroacetic acid can be used to acylate enol ethers. Trifluoroacetyl chloride boils at -27 degrees Celsius, while the anhydride has a boiling point of 40 degrees Celsius and is therefore easier to handle in the laboratory. This here is such an example with a fluorinated acetic anhydride as electrophile. The reaction was slower than in the previous example, but still a good yield of the enone was obtained. Interestingly, enol ethers may sometimes be generated in situ from acetals if two equivalents of acylating reagent are used. Here, the acylation occurred with high regio and stereoselectivity and in high yield. Because 1,2-dicarbonyl compounds such as alpha-ketoesters readily decarbonylate thermally, oxalyl chloride can sometimes be used as synthetic equivalent of phosgene. In the example on this slide, oxalyl chloride was used to convert dihydropyrane into a carboxylic acid. Here, the intermediate enone was obtained without the use of any base. In order to attain high yield of carboxylic acid, though, it was necessary to carefully remove the excess of oxalyl chloride prior to the thermal decarbonylation, because otherwise, instead of cleaving off carbon monoxide, the intermediate enone cyclized to a lactone. This is an example of palladium-catalyzed benzoylation of a vinyl ether. Unfortunately, palladium acyl complexes can decarbonylate when heated, and this led to the formation of arylated enol ethers in this instance. By the way, vinyl ethers are acetaldehyde enolate equivalents and are prepared on a large scale by addition of alkoxides to acetylene. Acetaldehyde is difficult to handle because it boils at 20 degrees Celsius, is highly flammable, and readily forms 3- and 8-membered cyclic oligoacetals upon contact with acids. Because acetaldehyde is quite acidic, the ionic enolates of acetaldehyde show low nucleophilicity only, and few successful reactions of acetaldehyde have been reported. Vinyl ethers, as the one of this example, are easier to handle than acetaldehyde, and their chemistry is therefore being studied thoroughly. Alkoxyenones are useful intermediates for the preparation of pyrazoles, pyridines, and other heterocycles, which in turn are important substructures of agrochemicals and drugs. So what can go wrong? One set of side reactions originates from the sensitivity of enol ethers toward acids. These can cause enol ethers to oligomerize and various nucleophiles to add to the enol ether, such as halides or alcohols. Because only highly electrophilic acyl halides react with enol ethers, the use of acyl bromides or iodides may also be considered. I could not find any example of the acylation of enol ethers with acyl bromides, but with acyl iodides a number of unexpected products are formed. In this example, no enone was obtained, and instead a number of other products such as vinyl iodide and vinyl acetate were formed. So there is currently no simple, high-yielding method for acylating enol ethers with derivatives of normal, non-halogenated carboxylic acids. Here are a few more examples of enol ether acylations. One related type of chemistry, which has also been thoroughly investigated, is the acylation of enol esters in the presence of Lewis acids such as aluminum chloride or boron trihalides. With structurally simple substrates, these reactions sometimes work well, but a good method for purifying the product is usually required. Often, numerous byproducts are formed with similar properties as the target compound.